Oh, all right. Here we go. So, what we talked about last time, well, was matter, which is like everything. And then we talked about how matter is sort of classified, right? We've got substances, we've got mixtures, and substances are really what we dug into last time when we talked about the differences between a compound and an element, right? Element, the purest darn thing you could ever get. All the atoms are exactly the same. Compound, on the other hand, that's where you get two elements and you chemically combine them, two different elements, and those properties change wildly, right? Like hydrogen explosive. Let me fix my doobly-doo here. Hydrogen is explosive. Oxygen is explosive. You put hydrogen and oxygen together, and you get water that puts out fires. So, life is a weird thing. So, yeah. So we're going to keep on going on, and I think the next thing we're going to talk about here is the development of the model of the atom. Right, now here's the thing. It's important to realize that it took, I want you to really pay attention to the dates and how long it took for this stuff to happen. Because none of this is really obvious, right? We have been working on this for our entire human existence. We've been asking, what are we made of? What is this world made of? And it's taken quite a bit of time to figure that out. So what we're doing today is we are going to go through the history of the development of the model of the atom. Why is it important? Well, this is the evidence. This is the proof, right? The proof, evidence, hard evidence that these things exist, and this is how we got there. And I think it's also really important to see how over time, one of the most important things of science is that our models of the world change. We're open to new interpretations of the world based on new evidence. So this is how the scientific method kind of works. We make an observation, we form a hypothesis, we test it, we observe the results, we reformulate our hypothesis, we test it, so on and so on and so on. And one of the key things about science is that we are open to changing our interpretation of the world. So if somebody is able to prove something wrong, it's going to ruffle some feathers. However, as scientists, we need to keep our minds open to new things, to new changes. So, atoms, the history. The theories of atomic structure have been going on since forever, and we're still digging into it today. I mean, really. However, the things that we're going to be learning in this class are it's pretty well solidly entrenched in the things we're learning here aren't going to change. They've been pretty much proven over and over and over, and nobody's ever been able to break it. So the stuff we're learning right now, pretty good. There are still some of the things on the edges of atomic structure that we are still working on, like nuclear stability. We don't really have a solid idea and understanding as to what makes one nucleus stable and another one not. It's just a thing, This wonderful part of the universe is you're going to have more to learn than you could ever imagine. We're never going to know it all, which is actually kind of comforting. We're part of something huge. Anyway, atom, Democritus, look at this date here, 480. Now, this is not the first time somebody came up with a theory of what the world is made out of, right? Like I said, we've been asking ourselves, what is the world made out of since we were humans, right? Probably since before we were humans. I wonder if my dog looks around what is this? What is this stick that I'm chewing on made of? I don't know. Who knows? But this is the first real solid recorded human thing where this idea that actually hit on truth. Now, Democritus had no evidence for this whatsoever. It's just an idea that he pulled out of somewhere. But anyway, he said he had this idea that there's this fundamental building block of nature that can't be broken down. Right? And the reason why he figured that is look at the building. The building is very big. Well, what is the building made out of? The building is made out of bricks. Well, what are bricks made out of? Bricks are made out of grit and sand. So there's and in grit and sand you can there's little teeny particles of that. So he figured that if everything else is made out of little bits of something, then there must be the smallest little bit possible, and everything is made out of that. And so he coined this word atom, I think it's pronounced atomos. Which means indivisible or unbreakable, right? Did he have proof? Nah, dude had no proof. Dude had an idea, it just happened to randomly fall on the right idea. Lucky him. So, look at the timeline for that. 480 BC to 1 8,800 years AD. That's like almost 2 millennia later. We finally get this guy, John Dalton. Now, John Dalton had proof positive. He had evidence that was repeatable. He could do it in his lab. He could bring it over across Yorkshire. He was English, so he would bring it across Yorkshire and do it over there and get the exact same results. He could tell somebody about, he could write a letter and send it off to someone over in France, and they could do the same experiments and get the exact same results, and wham! There you go. Repeatable proof, evidence. He came up with this thing called the atomic theory of matter. Now, if I may go on a bit of a tangent, I want you guys all to dial into this thing right here. This is an incredibly important word for us all to really, really know about, because it is being misused horribly in our day today. The word theory, when used by a scientist, does not mean a guess. A hypothesis is a guess. Most TV people and reporters and whatnot forget, I think they skipped high school science and forget completely what the word theory means. So when a scientist uses the word theory, this word here, this word theory, what it means is it is an explanation of natural phenomenon, of laws of nature. It's an explanation of how laws of nature interact to produce a phenomenon. For example, it is referred to as gravitational theory. It is not referred to gravitational theory because we're not certain if there's gravity or not. Dude, there's gravity. It's there. The theory of gravity explains it, right? So when someone says, well, it's a theory of this, it's a theory, they don't even know if it's real. They're just, dude, that person doesn't know a thing, and you should stop listening to that person and walk out the door or turn off the television because they have no idea what they're talking about. A guess or something that they're not sure of, that is a hypothesis. And it's getting kind of important for your generation in particular to really dial into this thing, where when a scientist uses the word theory versus some talking makeup face on some ridiculous news and opinion situation. It's ridiculous. Anyway, theory is an explanation of natural phenomenon based on natural laws, based on laws of nature. Okay? Theory means explanation. That's really what theory means. So here is what John Dalton came up with. Now, believe it or not, John Dalton ticked off everybody. He made everybody mad. There's nobody he didn't tick off with this one, because it shook the foundations, right? It shook the foundations of everything. Here's why. So he said that all matter is composed of atoms. Okay? So back in the day, they thought that, there's 5 elements, that things are made out of fire, wind, and wood, and water, and that kind of a thing. Where he was like, no, things are actually made out of atoms. And that ticked off that whole group of people. And what are they? They're these very small individual pieces of matter that we just can't break down any more than than those, the atoms. So they're like the little building blocks. The next thing he said, now this angered some people, is he said that all atoms of the same element have the same properties, kind of no matter what. Okay? So what that means is that if you have a piece of gold over here, it is the exact same as the piece of gold over here. So if you have a piece of gold that is just a circle, it is exactly the same as this other piece of gold that is in the shape of a holy relic that has holy water sprinkled on it. It's not going to stop bullets because it's just a piece of gold. So that's one of the things that he said. It doesn't matter what happens to it. It behaves exactly like gold no matter what it is. And that made a lot of religious people very, very angry. Very angry, because they believed that you could do things to elements and things to make them behave or act different, right? Made people quite mad. Now, this is another one that ticked off the scientific community, believe it or not. Atoms cannot be created, destroyed, or subdivided. Now, at the time, the scientific community believed in things like spontaneous generation, where if you wanted to create maggots, you put meat out and wind blew across it, and maggots spontaneously generated out of the interaction of raw meat and wind. That's what they thought. So, so of course they were like, well, of course things can just appear. That's how maggots just magically appears. So he was like, no, maggots have to come from something based on my observations that are right there in front of you.
Good morning.
Ooh, hey, hold on a second, guys. Gotta pause for the pledge. Okay, so anyway, here we go. So what was I saying? Oh man, it's okay. It's Miss Shirley. Not even mad. How can you be mad at Miss Shirley? Miss Shirley goes the best. Anyway, here we go. So yeah, atoms can't be created or destroyed. That made the sign. So over here, he's like, all the elements of all the atoms of one element are the same no matter what shape they are, no matter what you sprinkle on top of them. That made the religious community very mad. There were also people making a ton of money selling bulletproof relics and things. And over here, this one, he made the scientific community because he was like, you're wrong. And you're like, oh, I'm always right. I'm a smarty science guy. And you're like, well, you're wrong. So he made everybody mad with this one, dude. Like, everybody got mad. And so anyway, the last thing he came up was this one. It said atoms of different elements combine in whole number ratios to form these things called compounds, right? And what that meant was, or what he discovered, is that the ratios are whole numbers, right? Whole numbers. So what he kind of was able to figure out using some math and some really amazing ingenuity was that these atoms don't really break apart. They always shuffle around in these whole numbers. Like it's always 2 hydrogens and 1 oxygen, or it's like 1 carbon and 2 oxygens, or it's like 1 carbon and 4 hydrogens. It's always whole number. He could never get it to be like half of an atom. It always wound up perfect. The math was perfect every time, so that there were never any half atoms. Nothing ever subdivided or anything. So that's where he was able to come up with this thing that it's always whole numbers, always whole atoms, right? And that's where it also helped support this one, where atoms can't be created or destroyed, because he was never able to come up with a partial atom, right? They always stayed together and whole. And if he started out with 5 grams of reactant, he ended with 5 grams of product. Every time he couldn't unbreak it. And so he put out his information and his research and stuff, and people were like, oh, you're wrong, I hate you. And so they went in the lab and tried to prove him wrong, and they couldn't prove him wrong. Nobody ever could. Nobody could refute what he had, but what he did could be repeated over and over again, and they always got the same results, and his explanation really supported what happened. That's why they call it the theory. That's why they call it atomic theory, because it's an explanation of the phenomenon that they witnessed. Does that make sense? I hope so, because this idea of theory being a guess is like, oh man, it chaps my cheeks, man, because things are getting serious right now. So, moving right along. So here, this dude, John Dalton, this guy's the first dude to really nail down, there are things that are called atoms, right? And it only took about 2,000 years of our civilization to try to figure it out. Next, the big question was, what the heck are these things made out of? What are atoms made out of? What are they, right? I mean, of course, you answer one question, you open up 50 more, you open up 50 new ones. So this dude, J.J. Thomson, he was trying to figure out what are atoms made out of. And at the time, electricity was kind of new, so he was kind of playing around with electricity. And he discovered these weird things called electrons. And these electrons were coming out of matter, or atoms, right? So here's what he learned. He learned that electrons are negatively charged. So that's good to know. They have this thing called an electrostatic charge, static electricity, and it was negative. Why were electrons chosen to be negative? It causes a lot of pain in the butt, because, it just does. We'll see why later. I think it's Thomas Jefferson. I think you can blame him, because when he was playing around with and helping discover electricity, he noticed that there was a static charge, and he just needed to assign one thing positive and one thing negative. So he randomly and arbitrarily chose, this thing will be negative, this thing will be positive. And the thing that he chose would be negative, well, that's where all the electrons were going. So we ended up with electrons being negatively charged. Why? Because nobody knew what we were doing in the beginning. You're going to find, as we go through this class, things get named weird things, and weird things happen because scientists are just moving in the dark. They're blind because they have no idea where they're at or what they're learning until 10 years later when they finally figure it out. So, some things end up getting silly names. Anyway, electrons are negatively charged. They are also very small. When I say small, I mean like, woo, small, dude. Like, wow. And so J.J. Thomson came up with this thing called plum pudding. So when I say very small mass, I mean like the comparison is like if you could imagine somebody driving an 18-wheeler gets pulled over onto a way station and he's smoking a cigar. The smoke inside the cabin of his cigar is about how much an electron weighs if the atom itself is the 18-wheeler full of cargo. So it doesn't really weigh much. It's not going to make much of a difference to anybody. But they're there. They are there, and they do have mass. But it is unbelievably small. And so, plum pudding. The idea here is that, okay, well, if electrons are negative, then what does the atom have? And electrons are coming out of an atom. What does the atom have to be? Well, he thought, oddly, that, he had some idea that maybe atoms are solid because, everything is solid. So he was like, okay, maybe an atom is solid. These teeny tiny little solid big balls or things, I don't know. But if the electron part is negative, then that solid piece must be positive because it's neutral, right? Like, look, static electricity. No, there's no static electricity, normally, unless you make it. So if things don't have, a static charge, they must be neutral. Oh, I gotta get that. That's actually an important paper. So it had to be neutral because the world isn't one giant ball of static electricity, so the thing must be positive and the electrons must be negative, right? Right. Okay, so look, I'm going to walk you through his experiment here. So what is a cathode ray tube? It's like one of those old school TVs that are made out of glass. It's this thing. It's basically a big tube that is made out of glass, but it's been put through a vacuum, so there's no air in here. So electricity can fly through it really easy, like sparks and whatnot. Just go, just like right through. So what they did, remember he was playing with electricity. So he had this battery here, right? And this part is what we call the cathode, because this got loaded up with electrons. This is where the electrons were, right? This is the negative side of the battery, and this is the positive side of the battery. And because this tube was a vacuum, the electrons could fly from here right over to this positive one, and it formed a circuit, right? But what he did was he drilled a little teeny pinhole right there, right? And the reason he did that was so that, when these electrons come flying through, a lot of them would just splat here and make a circuit, right? So these guys would splat there and, current go, it's great. But once in a while, every so often, one or two would fly through, right? And then what happened is, we're going to pretend that these things aren't here, is it flew right through and it went dink right here and made a little glowy light. Now the glowy light thing is no different than anything, you guys have seen this before, this material on the back of this cathode ray tube glows when you hit it with electricity, just like the lights here in school, like those the fluorescent tube things. They glow when you smack it with electricity. It's nothing new or crazy. So that's how he knew that it was coming out of atoms, because it's coming out of this thing. How? Because electricity. So it's coming out of matter. So his question was, does it have a charge? What's up? So he literally just started messing around with it. And so he put these things on it, and these are electroplates. These are basically attached to another really, really big battery. Okay? So this side was positive, and this side was negative. So anyway, where were we? I was talking to you about this. So we went over here, and he attached these things, right? So this is a positive, it's just a positive end of a battery, and this is a negative end of a battery, but a really strong battery. So let's think about what would happen. So here's this little electron right here. It's coming through. It's just a happy little electron, right? It's flying along. It's just flying along. Now when it gets right about here, right? So here's the thing. You guys should know this about charges. This thing is a negative charge. So this plate down here is a negative charge. So like charges repel, right? So there's a force that pushes it up. because this is negative and it's pushing it away. It's like a repulsive force. And this plate is positive. Opposite charges attract, so there's yet another force pulling it up. So as the electron goes through this area, it is pulled up. You know what I mean? And so what J.J. Thomson could do is he could get these electrons, whoop, and he could get them to move up here. So when these plates were off, when this positive and negative plate were turned off, unplugged from the battery, he had a mark here. As soon as he turned them on, he had a mark here, which was definitive proof that whatever this stuff is, it's coming out of atoms, and it's negatively charged. And everything he did, he took these plates and they twisted them this way, they twisted them that way, they put magnets there because electric charge interacts with magnets, and everything it did behaved like these things coming out of matter were negatively charged, right? These teeny tiny little things. So this is what he came up with. This is his plum pudding model, right? Where this whole thing, the big thing here, is a positively charged atom, and there are these little tiny bits of negative electrons embedded. I like, plum pudding is like an English, he calls it plum pudding because he was from England, and like this is really like, it doesn't look appetizing, but it's like a pudding with like plums in it. It doesn't seem appetizing. I'm gonna go with chocolate chip cookie dough model because that sounds delicious. Like, you know, this is the chocolate chip cookie dough, and like the negatively charged atoms are the chocolate chips, just all embedded all in there. It's delish. So anyway, moving right along, we come up to Ernest Rutherford. So look at this date. This date was 1897, and yet only like not that much longer, 1911. Now we're coming up with the gold foil experiment. Man, so things are starting to move fast, right? Because the scientific method has been like established. The word theory, explanation, has been like established. There's a big difference between hypothesis and theory, and scientists were like dialing in on that. And there weren't talking radio show knuckleheads that don't know what theory, hypothesis. Anyway, Rutherford conducted this thing called the gold foil experiment. Now, in all fairness, it wasn't just him. Rutherford was like big brain. Big brain. He was actually really smart. And so he was he and some of his grad students, he had many people working for him, like doing experiments that he kind of oversaw. And one of them was like looking at radiation, because radiation was a new thing, so they were just kind of messing with it. And radiation went through stuff, right? Radiation just goes through things, like X-rays go through you. So they set up this experiment where they shot radiation at a piece of gold foil. Now I don't know if you know what gold foil is from crafts or arts or anything, but it's like it's gold. It's like actual gold element, but it's hammered down so thin that it's like gold leaf is really what it is. It's like only a few atoms thick, very very thin, incredibly thin. So he hung this piece of gold, shot radiation through it, and around the gold he put like what amounts to like old photography paper. Things that lit up when radiation hit it. It's like the old X-ray film, really. And what they expected, right, is they expected things to kind of go through the gold foil, right? But that's not what happened. So that's not what happened. That wasn't the data that happened. So Rutherford came back into the lab to these like grad students, and they're like, "I don't understand, Dr. Rutherford. Everything's all wrong." And he was like, "Well, do it again, but do it right and stop making mistakes." And off he went. The grad students set everything up again. They did their experiment. They got the exact same data. They called Rutherford over and like, "You don't know what's going on." And he was like, "What? What's the matter with you? Come on!" Like he's like, just make sure you're doing it right. And so he left, and the grad students set it up again. They got this exact same wrong results. And this time, Rutherford, when he came back over, he was like, Rutherford was actually kind of an awesome dude. Because instead of being like, "Oh, you stupid grad students, you're doing everything wrong," he was like, "Hold on. These people are pretty smart. They're probably not making the same mistake 3 times in a row. It's probably me who is wrong. It's probably not nature." Ooh, hey, my tie's off. He's like, it's probably not nature that's wrong, and it's probably not these young students who are like really smart who are wrong. It's probably me who's interpreting the results wrong, because he had an expectation of what it was supposed to be. And when he did a lab, an experiment, and the results were different, instead of saying, oh, my lab is all wrong and I'm all wrong, he said, oh, wait a minute, maybe there's something to be learned here. And there was. So they started digging into this, these wrong results. And man, did they break open science. What they were able to prove and demonstrate is that atoms are mostly empty space. Like the vast volume of an atom is absolute nothingness. It's not like it's air, because air is made out of atoms. It's the stuff inside of an atom is nothingness. It's mostly absolutely nothing. However, there is this dense, like the word dense, like doesn't even come close. There's a dense center, and that center has a very, very strong positive charge and almost all of the mass. So what that means is the vast volume of an atom, like if an atom had edges, most of it is absolute nothing, but in the very, very center there is this really, really dense core that has almost all the mass in it, and it has a positive charge. Right? So now we have a much different model than this solid ball of positive charge with bits of electrons in it. It was like there was this core in the middle, just like in a cell. So he called that core in the middle, he called it a nucleus, right? And then the rest of it was empty space, but the electrons were there somewhere. We didn't quite know, but it was almost all nothingness, which is like, what? So even things that are solid, right? Like the reason why radiation goes through stuff is because atoms are almost all nothingness, almost all empty space, nothing, just pure, utter, like it's hard to wrap your brain around nothingness. Like I think the analogy they like to use is if there was an NFL football stadium, if you had a ball the size of an NFL football stadium, all of that would be empty except for the nucleus, which would be the size of like a marble floating in the middle, and the rest of it, absolutely nothing. Just like, what? So this is his experiment, and I need you guys to really dial in on this experiment in particular because it was so like earth-shattering. People like to look at this one. And so this is what it was. This is basically a big lead brick with an alpha emitter. So an alpha particle is a kind of radiation that, compared to radiation, is huge. I mean, like huge, okay? So, big radiation. And then there was this teeny little pinhole so that the alpha radiation, when it came out, right, it was just like, it was just a beam. And so the beam of radiation came out and smacked into this gold foil right here. You guys get what I'm saying? Now there's two schools of thought. One is if an atom was solid, if it was a solid thing, what would you expect to happen? Well, I mean, think about it. Like, where's a wall? There's a wall. There's a wall over there. If I threw a tennis ball at that wall over there, what's going to happen? It's going to bounce back. Right? However, if it was an illusion, or if it was like, if it's smoke or fog, that's a much better. If it's fog, if I took a tennis ball and I threw it at fog, what's going to happen? Yeah, it's going to go through the fog because it's fog. You know what I mean? It's like, so it's no different for atoms. So here's the thing: if most of the radiation goes through, like almost all of it goes through, that means almost all of an atom is like fog or mist. However, some, and some, like very, very, so few, instead of going through, actually ricocheted straight backwards. And what's even more baffling is that some didn't necessarily ricochet sideways, but instead took like an asymptotal sort of trajectory. So what I'm saying is, as the radiation came in like this, instead of colliding and like ricocheting off directly, what it would do is it came in and it had this arcing curve like that. And how was he able to tell that? Well, not only was he one of the world's leading scientific minds of all time, and not only was he one of the greatest experimental designers literally to ever live, he was also one of the best mathematicians walking the earth. So he was able to figure that out using math, that the trajectory of these particles was not like like a billiard ball coming in, colliding, moving off at one angle, but instead have like an asymptote sort of trajectory, which is why you learn stuff like that in math. So if you ever turn into Rutherford, you know why. So what does that tell us? That tells us that because most of it goes through, most of this gold is empty space. Now, when they kind of like instead of ricocheting off, or sort of pushed off to the side, well, we know that this alpha particle has a positive charge. That's supposed to be a plus, not a T. And so if it has a positive charge and it's being pushed away, that means whatever's in the middle has to be pushing it away, has to be positively charged, because like charges like repel. Does that make sense? And then, if it's ricocheting directly back, right, these ones that came back did a path like this. Now they did a straight ricochet. These guys, the ones that like came right back. That means it collided with something. But it was so few that collided. That means that whatever's in there that it's hitting has to be really, really small. It's like it was like taking a shotgun and shooting like 10,000 rounds of a shotgun at something, and only like maybe 2 pellets actually hitting the target. It's a small target, like really small. And sure enough, it was. And this is what was going on inside that gold foil, right? So just sort of like a different angle. So this is what was happening with the nucleus. Let me go to different colors so you can see here. This is what was happening when it hit the nucleus. When it hit the nucleus, it came in, bam, hit the nucleus, and bounced right back, right? But you see, most of them just went through this empty space. Just like zung right through, zinging right through, zinging right through. Some were just sort of nudged down just ever so little. And some were sort of like nudged down a lot, or like nudged up a lot. And that's where he was able to find, like the fact that they were nudged as opposed to colliding, he was able to see and show with math that they were being pushed away, not necessarily like having a collision. I don't know if that makes sense, but there it is. And so now the big question is, all right, so where are the electrons? That was the question. Along comes this guy, Bohr. Bohr is like, man, this dude's crazy. This dude right here, look at this guy. Look at that guy right there. Oh, young gentleman. Totally illiterate. Couldn't read. Dude couldn't read. Because he was so dyslexic. And back in the day, like even when I was a kid, dyslexia was not a thing. You were just told that you're dumb and like written off. But this guy fortunately had some teachers that were like, he can't read, but this dude is sharp. So he did make it through school, and when he went to college, the dude brought his mom with him, and his mom lived in his dorm. His mom was his roommate. But what happened was, his mom read him the textbooks, and he just memorized the textbooks. Who does that? Well, Niels Bohr does that. Wonderful man, very like hospitable, kind, always welcoming of people who wanted to learn, and he was like, I think one of the things that made him so wonderful is that the fact that he had dyslexia and was basically illiterate for like almost all of his life. He really understood what it was like to not understand something. And so he knew what it was like to have people look at him and be like, oh, you idiot, you don't understand. He knew what it felt like. And so he never wanted to like do that to someone. And so he was like, turned out to be this like really wonderful, open, welcoming guy who basically was happy to sit down and explain anything to anybody at any time in the most welcoming way possible. This dude literally changed all of humanity in ways that I can't even begin. But he got curious about hydrogen and what are electrons doing, and he came up with this thing called the planetary model. And this is the picture that you see all the time about atoms. It's wrong by this much, but so much was right. It's kind of unbelievable what this guy was able to do in 1913. Dude, I don't even know if they had cars in 1913, but this guy was like breaking down the universe. So anyway, here's his idea. Because he's like, okay, if the nucleus is in the middle, the electrons must be orbiting like planets around it. Because when he looked out into the universe, that's what he saw. He saw things in the middle, like the sun, and other things like orbiting them. Right? Like planets orbit the stars, the moons orbit planets, the planets are like orbiting inside the galaxy. So yeah, that's kind of what he thought. He was close. So for him, this was the nucleus that where all the positive charge was, and what he thought is that electrons were these negative things going around circles, like around the outside, around the outside, around the outside. Negatively charged electrons go around the outside. Kind of close. And he figured all this out by like making hydrogen gas glow and putting that light through a prism. Oh, and then mapping. He was, again, mapping. Mapping is huge. So here's what he said. He said electrons orbit the nucleus like planets around the sun. Now, this is the only thing that he got wrong. That is it. Everything else was absolutely right. The next thing he said is that electrons have fixed energy levels, or like places where they can be. And they gain or lose fixed amounts of energy, EMR, in the form of EMR, or light. Okay, so what that means is these energy levels are fixed. It's not like, it's like there are tracks where these electrons live. And they are in one track or another, nowhere in between. Why? Because there's nothing to support them there. Does that make sense? And they go up or down in these energy levels through the use of EMR, which is electromagnetic radiation, which is light. You know, like red, orange, yellow, green, blue, that kind of thing. So in his model, N equals the energy level, where N equals 1 is the lowest energy level, like 1 is the first floor of a skyscraper. If N equals 5, that's like the 5th floor of a skyscraper. Okay? And they can move up and down by absorbing, goes up, and releasing, goes down, electromagnetic radiation, or light. Okay, just like if you were in a skyscraper and you went from the 1st floor up to the 5th floor, it takes energy to do that, right? Like you have to put energy in. Now, if you were to just jump out from the 5th floor and just jump out the window, energy will come out of your body. I hope you brought a parachute or something, because that would be bad. So what that gives us are two things. Two new things. We have two new things to deal with. First is called the ground state. And this is where electrons are at their lowest energy. This is where electrons start. Or where electrons are found normally. This is their normal state. This is like regular. They haven't absorbed energy. They're just chilling, right? That's just what they do. This next thing is called excited state. This is a state where electrons absorb energy and they occupy a higher level. They jump up. Right? It's like when you get into an elevator, that elevator puts potential energy into your body as you lift up. Light, when it hits an electron, that electron absorbs that light and jumps up a level. Now, a little teeny fun fact is that if you jump up in the air because you're excited, you pretty much automatically fall right back down. Same exact thing happens with electrons. As soon as they absorb energy, they jump up to the excited state, boop, but then they fall right back down. And when they fall back down, they spit out light. So they absorb light, like one color of light, to jump up, and then they fall back down and they spit out a slightly different colored light. Fun stuff. It's how black lights work. Super awesome. Super awesome. Okay, so what? Oh, wait, it's over. That's all I've got for you for today. Now, that's the historical development. The actual, modern model is actually close to the planetary model, but not quite. Not quite. So that's how we got to where we are with, the nucleus and being positive and in the middle, and electrons being negatively charged and super small. And how can you possibly say that an atom is mostly empty space? There it is. I mean, proof positive. You can take a particle that's the size of, a school bus, and you can throw it at atoms, and it just goes right through. Atoms are mostly nothingness. So, homework, classwork, the thing that we're going to be working on are 3. We got 3 of them now. 1, what are atoms? That is one of them. And then there's understanding the Rutherford model, where we are going to dig into it and really work our noggins with the Rutherford model, and then taking it a step up, we're going to work on understanding the Bohr model. You got it, guys? I hope you do. This is what we're working on. Happy end of this video. Hope to see you soon. All right, guys. Have a good day.